Hi everyone, welcome to another episode of Monroe Live. Today, and partially above me, is something exciting that we've been waiting a long time for. So we're going to be reviewing the underbody of the Lucid Air. So we just got this in a few days ago. A group of us have just been poring over, looking underneath this. Frankly, there's so much content, I think we could probably do 3 to 5 videos just talking about all of it, because I've got a question or a comment on just about everything that we're looking at here. I'll try and keep it focused on the wave tops here as we go through. So hopefully you found it or you find it as interesting as I did. So we're going to kind of start at the front of the vehicle and work our way rearward. We may even break this up into 2 videos, but we're going to start with the front and see how far back we go. And stay tuned. So starting with the very front of the vehicle, if you've seen any of the tech talks from Lucid, the Peter Rawlinson gentleman, he does an excellent job at articulating some of this. We can now see physically in person here, we've got these ducts coming in through the front AGS. AGS are the active grille shutter systems, right on the left and right hand side of the radar module here. And so these are taking in air, these are diverting air directly to the 2 radiators, left and right hand side. So this vehicle, unlike most conventional vehicles, it does not have a downturn radiator, doesn't have a vertical radiator module or anything like that, but rather it's got 2 radiators outboard of the primary rail sections. Typically, having those radiators outboard of the rail sections like what we see here in times past on ICE applications was reserved for what we would refer to as like low temperature radiators that were for turbocharger cooling, auxiliary cooling, or additional, like a good reference point would be like BMW used them for the turbochargers. But if they were truly just additional cooling capacity, the Gen 6 Camaro with the 6.2 liter V8 setup, they ran them in series, those low temperature radiators on the outboard side to the primary radiator in the center, simply because they didn't have enough heat rejection given one single radiator. So lots of different ways to utilize this space from a radiator perspective. But in this case, on the Lucid, they've used these as their primary radiators for all of the ethylene glycol or the coolant-based systems in the vehicle. So one interesting thing here, separate from the fact that we've got outboard radiators, is that they actually created, think of like the inside of a wave with a surfer, right? So it's like that real, like a tube style duct coming from the outboard side to the inboard side as we get to the radiator. What that does is it creates like a vortex, and then that also is helping create turbulent air. Turbulent air is going to be more effective in terms of heat exchange as it goes across the louvers or the fins of the radiator to optimize the efficacy or the heat exchange of those radiators. So simple, but kind of elegant at the same time in the way they executed it. The other major benefit by putting these radiators outboard is packaging space. I can't say enough for packaging space about this vehicle. Everywhere that we've looked thus far, it's incredibly tight. It's like the spacing between the hoses versus the hard component modules versus structures and all the rest are incredibly tightly packaged. So much so in some cases, and I'll point a few of them out, it's almost cause for concern because they're violating what we would call design practices that many OEMs would just flat out say, nope, not going to happen. So that packaging space, you know, the radiators are part of the enabler to increase packaging space. But one primary benefit from that is their frunk size. So if you look right here, and you see this ribbed structure that I'm pointing out with the laser here, that's actually the bottom of the frunk tub. So relative to vehicle size, this frunk tub is, I would say, world-class in terms of vehicle size versus frunk volume. It's actually astounding how much frunk volume this vehicle has. But that is enabled by this whole front end package and how tightly everything is packaged on the front end. And on the back side, which we'll get to in a moment, it's enabled by how tight and small the motor, the charging module, DC to AC, and the power distribution center with all the relays and fuses and so forth, how spaced out those are fore aft. So kudos to Lucid for packaging those so tightly. Now, as I was talking about trade-offs and maybe some areas for potential concern, this is one of those specific areas. So as we look at those coolant hoses, specifically right here, you'll notice that there's a constant tension band right next to this T-fitting right here that is rubbing directly up against this other hose. The problem is there's no separate bracket to keep the relative movement between these two stabilized. And so over time, what's going to happen is that these are going to rub together, and if left long enough and driven long enough, those have a pretty strong tendency to start to wear through. Most OEMs that we work with would just flat out say, nope, not going to happen. They've got design rules and practices so as to mitigate areas of concern like what we see here. Okay? So, Lucid is what I would consider a startup company. One of the things with startups, and it seems to happen every time we get a startup in the building, Rivian, Model S, the Model X before that, the original iterations, what we see is a multitude of extruded and MIG welded or a bunch of pieces, a lot of piece parts, right? Discrete parts within the vehicle. The entire front end, as we're looking at all of these pieces, if you can kind of take a moment and absorb what we've got here, we've got a stamped aluminum lower shield that is riveted to the cradle or the primary front subframe here, and it's bonded additionally to the rivets with structural adhesive. This is probably 2.5 to 3 millimeters thick of aluminum, so that's not insignificant in terms of thickness. It is doing a lot in terms of being a shield, but there's a lot of labor and processing associated with individually riveting all of these in place, and to boot, having all the structural adhesive. Not only that, Lucid is also paying to get all of this painted. So even though it's aluminum, and yes, aluminum's prone to oxidization and so forth, but they're still painting that all black. So moving forward of that, and this is some additional piece count, as we look at these front crush rails, we've got an extruded aluminum member that sort of butts into the front of the cradle, where we've got two cast pieces that help support that crush member, more structural adhesive, more fasteners. And then as we go outboard, we've got this piece right here, which is a multi-piece stamped steel weldment that's multifunction. So it is connecting to the cradle. It's going pretty far forward in vehicle. It does appear to be within that small overlap rigid barrier, so IIHS, that 25% of overall vehicle width zone. So it's probably enabling their SORB script. It's helping with that to help divert the vehicle away from the barrier. But then it's also providing additional structure for these guys right here. So what these are, these two aluminum pencil braces, they're aluminum extrusions that are then pinched down at the ends to provide a perch for those fasteners to go through so that those aren't crushed when they're installed. That's supporting those radiators that I was referencing, which are outboard. So this is doing a few functions, which is great, but again, a lot of fasteners, a lot of piece parts going into that. As we move inboard, and I think we could probably go to the other side to take a look at this. As we move inboard and you were to look at the back side of the cradle, close to where those members all come together. Grace, you might want to swing around to this side here. You can see the large castings, that stamped weldment, the extruded crush cans in front of it, the control arm, the extruded portions of the cradle, all of these come together. So we would refer to this as like a node or sort of a nexus structurally, where all these different monuments from the cradle are coming together. There's more elegant ways to accommodate all of these features, especially given that they've got a casting here, but there's a pretty significant number of components that are all being fastened with different mechanical fasteners. So, as I mentioned before, it's not atypical for a startup to exhibit that number of fasteners, this many different types of processing, right? Extrusions, stampings, bolts, MIG welding, rivets, structural adhesive, right? It's not atypical, but in future iterations, what I would hope to see from Lucid is that they're really starting to hammer out some of that and get some of the cost out of this vehicle. Okay, and just kind of a sneak peek here, looking at the radiators on the backside, you can see these guys each with their own fan units mounted to that little carrier with those pencil braces that we saw. Now if we spin around and take a look at the suspension. So the suspension is actually pretty novel, or I won't say novel, I'm going to say it's pretty rare in the competitive set. In higher performance applications, you do see this a little bit more often, but still relatively rare. And by that I mean this is a SLA, so short arm, long arm suspension with a double virtual ball setup. And so I'll explain in a minute what virtual ball means. But in essence, we've got two separate arms for the upper A arm of the control arm. Grace, if you swing around here, I'll point out what I'm talking about. So right there, that's the forward upper control arm. And then the rear upper control arm is right there. It's going to be a little bit harder to pick out. But each one of those goes to their own ball joint at the top of the knuckle. At the bottom of the knuckle, we've got a similar setup, two aluminum control arms, each going to their own ball joints at the bottom of the knuckle. So in essence, we've got 4 ball joints all going to the knuckle. So let me go over to the whiteboard for a second, and I'll explain what I mean by virtual ball versus conventional. So in a conventional suspension setup, these are like a top-down view looking at what this would be, which is the tire. So a top-down view looking at the control arm, which we were just pointing out, going into the knuckle, right? And then this would be the pivot point. So in a conventional setup, you'll have 1 ball joint, and this, as you go through a corner, right, as you turn the vehicle, this is the point by which the entire front suspension corner and the wheel are going to turn about. And so what's happening is that entire wheel and tire are scrubbing through that corner. Now with a virtual ball setup, since we have 2 ball joints and they stop short of intersecting with one another, the reason they call it virtual ball is because what happens is if you were to draw a theoretical line continuing along the axis of those control arms, which are represented by these dots here, the actual pivot point for this control arm setup is further outboard than in the conventional setup by a pretty significant margin, right? Note, not to scale, I should say that. But if you were to look at a virtual ball setup, by getting this pivot point further outboard, this is a suspension dynamics enabler, right? It's going to give you better steering feel, better feedback, better control. It's going to keep your tire more planted in a multitude of driving environments. And then also it's going to reduce the amount of tire scrub that you've got on the ground because naturally it's going to want to turn better, right? So some enablers to doing virtual ball, but not without the cost penalty. On this setup, we now have 4 ball joints versus a conventional, which is either 2 or 3, depending on if it's a single or double virtual ball setup or just a standard single ball joint inner. So to kind of give everyone some background on what we mean when we say virtual ball. Now, since this is all-wheel drive, going back to the suspension here, the knuckle, right? Or I'm sorry, not the knuckle, what we'd call the shepherd's hook or the base of the shock absorber, which is this forged aluminum piece right here that I'm pointing at. And the point where the shock absorber is attached to it, which this is called a split joint, right? So the shock absorber goes into that split joint, the fasteners ran down, and that puts a clamp load on that. This whole setup actually goes around the half shaft. So you can see the half shaft or the drive shaft, CV axle, there's any name you want to pick, going outboard to the knuckle right here. And then if you were to swing around, what you can see is that forged aluminum piece actually forms like a C-clamp shape, or a shepherd's hook, however you want to refer to that. And so this is a way for them to, if you were to draw a line straight through the shock absorber to the lower control arm, which the shock mounts to, it's a way to keep all of those things in line. But this does drive some additional material because it's less efficient to make that corner structurally, right? So this piece, part of the reason it's forged is it needs to be significantly stronger than, say, a rear-wheel drive only, where you don't have a half shaft, and the load axes from the shock absorber can go straight down to the control arm. So some trade-offs there. If we look at the half shaft, I just want to make mention, the outer diameter, meaning the size of this joint, right? This is the end of the half shaft, is incredibly large. And you might wonder, why is that so large? It's because of the torque. This vehicle puts out an immense amount of torque. And the larger the OD, or the outer diameter of a given section is, specifically, and definitely is true with cylindrical sections, what this is, the larger that outer diameter is, the better that section or that half shaft is going to be able to manage the torque that's driven from the motors out to the wheels, and actually from the wheels back into the drive system, depending on the mode. So that is simply that size to help manage all of the torque coming from this motor back and forth. Okay. So moving rearward, if you look right here, you'll see this black injection molded tank-like structure right here. So that tank-like structure is serving as like an oil pan slash a cooling assembly for the gearbox and the motor, right? So you've got a gear oil pump right here that sleeves into the outboard side with a few fasteners, and then you've got your coolant coming in from the opposing side to help cool down some of that coolant. So what's interesting about these motors, they're about 600. They're rated for about 670 horsepower each. Not insignificant. If you've ever, you can go and take a look at the Lucid Tech Talks about their motor and their new tech. They're very cool. I encourage you to take a look at those. But the interesting thing here, we talk about commonizing things and maintaining commonality between different vehicle platforms and so forth. Well, they did something similar. They kept common motors front and rear, but with one small tweak, which is the orientation. So on the front motor, the inverter, so as to increase the amount of packaging space from the occupant to the motor or the spindle, however you want to phrase that, which is a very critical dimension in vehicle architectures, they rotated it such that the inverter is on top of the motor. When the inverter is on top of the motor versus the front or the rear, the X direction, right, the amount of space fore aft that is garnered, is whatever the inverter is plus whatever additional clearance is needed for that stack up, those assembly processes, and whatever their internal specifications are. So that's a huge enabler to making the cabin from wheel to wheel, axle to axle, the wheelbase, to make the cabin as maximized as possible given the technical elements that must be in the vehicle, the motor, for example. So that's what they did on the front, and then similarly on the rear, to maximize it, they took the inverter, and instead of going on the top, they rotated the motor and they put the inverter on the rear. So it's kind of an interesting setup. The one sacrifice they made is that these tanks, right, these injection molded pieces, are now unique because they've got very different packaging environments. When I was talking about how tightly this entire vehicle is packaged, one of the very distinct areas that you can look at to see what I'm talking about is if you see these kind of like little cutaways. They're not actually cut, they're molded like that, but I'm saying that figuratively. So these little cutaways, they mirror the shape of the battery flange, the battery pack flange above that. And so we're talking, less than 10 millimeters of clearance, which most OEMs will be in the range of 15 plus millimeters for decking clearance between major monuments. They're less than 10. They're incredibly, incredibly tight. And so they really took the concept of every millimeter every day to the maximum. And so it's difficult to manage, but if you can do it, kudos to Lucid for being able to package everything in such a tight manner. So that's interesting. And then I think the last two elements that I really wanted to talk about were the rear end structure, or the rail leading into the rear end structure of this whole wheel envelope. So one of the key elements that really enabled them to have a stiff and strong front body structure set up was that, Grace, if you swing around to where I'm at, similar to what we've talked about on Rivian, we've referenced Range Rover that did this, the Model S did something similar to this. What you'll see is this is a cast piece, right, the torque box casting coming from the cabin side of the vehicle that ties into the rail. You'll see a big gap or hoop that the half shaft passes through. As you go down, you see this cast portion of the cradle closes out that section. So what they've done, and I've mentioned this in other videos, what they've done in essence is if you consider the entire front of this vehicle a moment arm, there's a lot of mass, all your suspension loads, everything is coming through the front of the vehicle, which is essentially a big moment arm relative to the front of the vehicle. The taller that you can make and the more robust you can make the section of those rails, the shock tower, the whole body structure system, the stiffer that's going to be, which is going to be better for MBH, it's going to be better for driving dynamics and all the rest. The stiffer that you can make that entire moment arm, the entire front of this vehicle, the better off you're going to be. So by them closing off that open section in the casting with the cradle, gloving over that half shaft, what they've done is they've drastically increased that overall section on the front end, which is, if you look at how the vehicle performs, is providing some pretty significant benefits to them, just like with the Model S and presumably the Range Rover and the Rivian as well. So yes, are they adding more material? Without a doubt. Does this have drawbacks in terms of perhaps serviceability and so forth? Yes, but what I like about the way that they did it, so the fact that they did it, great, many people do it. What I like about the way that they did it is the cradle actually closes out from the underside. It closes out where that half shaft passes through from the underside. That is important because as we're talking about decking major modules to the vehicle, bringing up a battery pack, bringing up a suspension pack, doing anything of that sort, it is really, really important, especially as you go to higher volumes, to simplify the axis of installation, the number of fastening points, and the process overall. By closing out the half shaft from the rear, what it enabled them to do is maintain an intact front suspension module so that the half shafts, unlike on a Range Rover, for example, can be decked with the suspension assembly. So the entire suspension corner theoretically could be fully intact and then it be decked all at once, versus like on Range Rover, it gets sort of stick built in some regard because those half shafts need to be passed through that hole, which is provided to them by that cast section in the rail. So kudos to Lucid for both getting the performance and also figuring out a creative way to make sure that this thing decks properly. All right, everyone. Well, we kind of wrapped up the front end of the vehicle. We're going to pick up on the next part of the series here. We're probably just going to do a two-part, front and rear of the vehicle. So we'll pick up here where we left off. So please stay tuned and join us for the second series. Just want to say, and so that Corey doesn't get mad at me, if you would, go ahead and hit that subscribe button. Thanks for your time.